by the Department of IIEST Shibpur and Global Alumni Association of our institute, GAABESU. I, Sneha Murmu, faculty member of this department, welcoming all the audience who have joined today's event off and online. It is my pleasure and privilege to welcome you in this seminar. As you all are aware, the topic of today's lecture is about life cycle analysis of infrastructures. We are immensely grateful for having eminent engineer Dr. Nirmala Bandyopadhyay as the speaker in this occasion. He is an inspiration and a role model for all of us. We once again welcome you and thank you for participating in today's event. To begin with the inauguration, may I start with inviting the honorable dignitaries on the dais. I request, it is my great honor to welcome Dr. Nirmala Bandyopadhyay to grace the dais. Now I invite the President of GAABESU, Mr. Amitabh Datto, to come to the dais. I also request Professor Arun Dev to take his chair on the dais. Now we look forward to the head of the Department Civil Engineering, Professor Choitali Ray ma'am, to take her chair on the dais. Please join me welcoming the dignitaries with a huge round of applause. Now I request our student, Ms. Shimon Naguri, to felicitate the, our guest of honor today, Dr. Nirmala Bandyopadhyay, with a flower bouquet. Next, I request Payal Vishwas to felicitate Mr. Amitabh Datto, President of GAABESU, with a bouquet of flowers. I once again request Shimon to felicitate Dr. Arun Dev with a flower bouquet. I request Payal to felicitate Head of the Department, Choitali Ray ma'am, with a flower bouquet. Now, I would like to invite the Head of the Department, Civil Engineering, Professor Choitali Ray ma'am, for welcome address.
Respected President of Global Alumni Association, IIEST Shibpur, Mr. Amitabh Datto, distinguished speaker and eminent engineer, Dr. Nirmala Bandyopadhyay, respected Professor Arun Dev, respected members of Global Alumni Association attending offline and online, distinguished guests of the dais, my respected teachers present here, esteemed faculty colleagues, and my dear students. It is my privilege to welcome you all to the 5th Professor Pradip Kumar Ray Memorial Lecture, jointly organized by the Department of Civil Engineering and Global Alumni Association, IIEST Shibpur. I would like to express my sincere gratitude to the Global Alumni Association for generating the endowment fund to organize Professor Pradip Kumar Ray Memorial Lecture jointly with the Department of Civil Engineering every year, and thus providing us with an opportunity to pay homage to our respected and beloved Professor Pradip Kumar Ray. Professor Pradip Kumar Ray, a commended professor with unique personality, was born in Chinsura in the district of Hooghly, West Bengal on 5th December 1943. After higher secondary examination in the year 1960 from Hooghly Collegiate School, he has secured first position in the district and second in the state.
ওরা হিন্দু সমাজের দলে বাঁচে তাদের বিরুদ্ধে সে যাবে না
Graduated from the then Bengal Engineering College in the Department of Civil Engineering in the year 1965. Soon after graduation in 1965, Professor Rai joined as a senior fellow in the Teachers Training Program. Subsequently, he obtained his master's degree in the Department of Civil Engineering in 1967 with two gold medals. In 1968, he was selected as a lecturer in the Civil Engineering Department through Public Service Commission, Government of West Bengal, as B College was then a government college under Calcutta University. Thus, B College got a great professor who served his alma mater with extraordinary intelligence, stupendous ability to handle all sorts of critical circumstances related to academic and administrative matters. He devoted his entire life for the welfare of the institute. In 1975, he went to IIT Roorkee for his doctoral study in QIP program and obtained his PhD degree in geodesy in 1979. Professor Rai continued his service as a faculty member in the Department of Civil Engineering IIST Shibpur till 31st December 2003. He was the head of the department during 2000 to 2003. He also took the charge of registrar, professor in charge of students' activities, PIXA, the accounts officer, the president, athletic club, so on and so forth. And he handled all the responsibilities with utmost sincerity and efficiency. Sometimes he handled two or three posts simultaneously with extraordinary capacity of handling adverse situation. It needs a special mention about his leadership to form a proper shape to the Board of Joint Entrance Examination as well as Central Selection Committee West Bengal. Even after his superannuation, he was closely associated with this department as a visiting professor as well as the external expert for the doctoral committee in civil engineering department. Other than academic and administration, he had an outstanding personality with a brilliant sense of humor. I am fortunate that I got him as a teacher and as a colleague. All his students know how exceptional his teaching used to be. He had the extraordinary ability to explain apparently complicated topics very easily and effortlessly. That teaching learning process was a real wonder for us. He had been always accessible to his students as a teacher and to his colleagues as a senior colleague. Practically, he was the master of all subjects in civil engineering. Countless friends, students, colleagues were thus benefited by his selfless and untiring help, sympathy, and active support. It was really a mystery that he never seemed to be overloaded with all his responsibilities together. He seemed to enjoy his workload, and it was always reflected on his glowing and ever smiling face. This was only possible for his selfless character and boundless love for the alma mater. His greatness has earned him homage from the vast multitude of his students, friends, and acquaintances, the homage that normally is paid to only a legend. His love for his alma mater and overall contribution to the institute is immense. It would be an understatement that he has given his life for the cause of the alma mater. A person like Professor Rai is few and far between in any era. Thank you.
Thank you, ma'am. Now I request President of GAABESU, Mr. Amitabh Dotto, to brief about the Pradip Kumar Ray Memorial Lecture and GAABESU.
Good evening. Welcome everyone on the dais as well in the front. It's a pleasure. This is the fifth year for this lecture, which we could jointly do with the department from the GAABESU end. In fact, similar program we have also started with the electrical department. There is one lecture took place few months back, and we are hoping to continue the way with that. It was basically a memorial lecture for all our beloved professors in the different department. Of late, we have another request came from electronics department that why don't we support them to create a similar program, a lecture program for the professors in that department. So it is our open welcome to all the departments, wherever it will be our pleasure to arrange and organize jointly with the concerned department for similar lectures. I will not extend much of this. Our only thing is we always are open from the GAABESU end to the students that whatever we can contribute for the students for their benefit, we utilizing our resources. We have enormous resources of lot of senior experienced professionals, and it is always welcome that whenever there is an opportunity, please come forward. It is a request to all the department. We can certainly organize this. This is the one way of making a bridging in between the students and the ex-students. Thank you.
Now I request Professor Arun Dev to say a few words on this occasion.
It's a real pleasure to be here today at the fifth Pradip Kumar Ray Memorial Lecture. Pradip was my student, and I know him very, very well. He is from Chuchura. I am also from Chuchura. Therefore, I used to know him long time. And he is helping anybody out of the way whenever asked for. I was in the United States at the time he passed away. And I was shocked because I did not know his health situation. Even 6 months before, when I was here in Kolkata and involved in GAABESU, he became involved in GAABESU. He used to come all the way from Chuchura to attend meeting to help us in GAABESU. Whenever he commits something, he actually did that. Another thing is, I was in America, and a friend of mine, his son was studying here and not doing well in studies. Then he asked me whether I can help anywhere. I'm in America. I called Pradip that such and such person needs help, student needs help. Could he help? That is obvious he started to help. Unthinkable that a person can do this kind of thing always. Pradip was always in my heart, and I was fortunate to give this lecture, Pradip Kumar Ray Memorial Lecture, second one, and I was fortunate and I loved it. I hope you all will enjoy this current talk, life cycle analysis of infrastructures, which is very critical subject. Whenever we talk about any project, we need to analyze life cycle cost. And Dr. Nirmala Bandabadda was also my student, and I know him very, very well. And thank you all for coming and joining here. And Nirmala.
Thank you, sir. Thank you for your valuable words. Now I request Professor Pradip Kumar Ray, faculty member of this department, to say a few words in this occasion. I also request all the audiences who have joined us online today to keep themselves muted.
Good evening, Dr. Nirmalo Bandyopadhyay, Mr. Amitabh Datta, Professor Arun Dev, Professor Chaitali Rai, senior alumni, students, faculty members. It is my great pleasure and privilege that I am able to tell something in this August gathering. Professor Kumar Ray, it is a name. It is whenever anybody of his student, any student, whether he is a senior batch or junior batch, everybody can remember him very well. His this is not due to only due to his high intellect efficiency, but also his human face. And every time, in every problem, he was with every student. Every student considered him as his guide or mentor or any way that you may say that it is the guardian. I met him as a teacher. He was my teacher in two subjects. Definitely one of the subjects that his subject, that is surveying. Also, he taught what I can remember, that project planning, that topic he also taught us. But I learned much more when I joined here as a faculty member. I worked with him, and different aspects he guided me in. I cannot express that how he has helped me. He has shaped uh, my stay here as a teacher. It is very difficult for me to express that how he is with me. Now, when I was the head of the department, I was fortunate that the first Pradip Rai Memorial Lecture was started at that time. I can remember Dr. Partho Chakraborty, his Professor Rai's batchmate. He was the first speaker in this program. Though the initiation was started before I took that, I became the head. Long before that, I think at the time of when my predecessor, Professor Chakraborty, was the head, at that time the initiation was taken. But I was fortunate that in the first lecture, I was the head of the department of this, and and it was organized with all what everybody was very much enthusiastic at that time for this lecture. And it is nice that it is continued, and now we are in the fifth memorial lecture. And we are also fortunate that today we are having a person like Dr. Nirmalo Bandyopadhyay with us. He will deliver. He is such an alumnus that his fame is spread in across the batch. Though I have not met him earlier, this is the first time perhaps I am meeting him, but I've heard of him lot for a long time. So I think all of us, we are eager to hear from him, and I hope this will also our memorable lecture for us. Thank you all.
Thank you, sir. Thank you for your valuable insights. We are highly honored that Dr. Nirmalu Bandyopadhyay is amongst us today. So let me introduce him. Dr. Nirmalu Bandyopadhyay graduated in civil engineering from erstwhile Bengal Engineering College in the year 1973. Besides University Gold Medal, he was also recipient of the prestigious Old Centralian Medal and Slater Memorial Medal. He holds an M.Tech in Civil from IIT Kanpur and received PhD in Structural Mechanics from University of Massachusetts, USA in 1978. He has a professional career spanning over 50 years in the field of infrastructure design, Dr. Bandyopadhyay is a professional design engineer primarily in the area of bridge and structural engineering. He was the prime mover for design of large number of bridges in various parts of India and abroad. He has excellent exposure in multiple aspects of computer-aided design. He has been members of Indian Road Congress, board committees, and also been members of International Association of Bridge and Structural Engineers working commissions. He has published a large number of articles in various national and international engineering journals. All the audience are eagerly looking forward for his lecture. Hence, without any further delay, I invite the guest of honor, Dr. Nirmala Bandyopadhyay, to start his talk on the topic life cycle analysis of infrastructures.
এটাতেই ভালো হয় তো? শোনা যাচ্ছে? হুম, ওকে। Thank you, ma'am, for your kind words. Actually, I feel honored to be invited to speak in an event associated with Professor Pradip Ray. Actually, Professor Rai, was a junior teacher when we were students, and Pradipda was more than a teacher. He was a friend and mentor. And in those difficult years of 70s, early 70s, I mean, we really got a friend. So I'll start talking about life cycle analysis of infrastructure. And I'll speak it mainly from a designer's point of view. That is, what are the design approaches that we normally take and what we should do. You know, the initial uh, design approach, what we do is that minimum initial cost design kind of approach. I'll talk about that. Then we graduated a little bit into the minimum life cycle cost. That is the cost of the whole project, whole structure throughout its life, whether that should be our goal to reduce that. And finally, integrated life cycle analysis, that is not just cost, but also consider the other aspects, primarily the environment. So these are the three parts in which I would like to give my presentation. Now, what is the conventional design process that we have all learned and mostly we practiced? We have a set of functional specifications. What are the requirements? Based on that, we size the system. Then we have these design codes. Based on that, we size the individual items. We work out the construction details and cost. We compare that cost of various such alternate designs that we do and select the design with the lowest cost, which is actually the low cost of only the initial construction. And without any considerations directly to whatever effects it would have later on in its lifetime. Although with this approach, I must say that we have great designers and we have designed outstanding structures with that concept. Thereafter, came this idea of life cycle cost. Now, what is life cycle cost? Is that a public infrastructure, a bridge, or say even this building? I mean, it's a long-term, multi-year investment. Following its planning, design, and construction, a building requires periodic maintenance, possibly repair and rehabilitation, and that might, uh, you know, go through even 100 years, a century, that might stay. And there are a lot of expenses involved while carrying out these functions, maintenance, repair, rehabilitation, to keep it, to make it, to make it function safely. So it's considered that it's logical to consider the whole life cost instead of just the initial cost to evaluate a particular option. So the life cycle costing, which is LCC is normally called, it presents a rational method for carrying out that same uh, effect. In a specification-based initial cost-based design, these concepts are indirectly considered with the introduction of the requirement of durability, life of structures, etc. When we say, when we design a concrete structure, all those, those concepts of that crack width, that it should be for various environments, the crack width should be this and that. They are basically, uh, you know, uh, talking about durability and hence long life of the structure. And why we want a structure to be not just minimum cost to build with is that once you build something, whether it's a bridge or a building, then the more number of years that we use it, it will be the better utilization of our money. Because otherwise, then we have to replace it, and replacement again you have to incur that cost. So in life cycle cost, we considered everything. First is that acquisition cost, which is the land cost, the building cost, and the professional cost. All of them. That's the initial cost. And then the operation and management costs, which is the maintenance cost, the service cost, the energy cost. I mean, in a bridge type of structures, once you build it, you don't have much energy requirement after that, after the structure is built. But once you have a building type of structure, then what happens is that your major expenses would be after the building gets into use. Your electricity costs and the water supply, sewerage, and all those AC ventilation, all those effects, I mean, all those expenses you have to go on doing year after year. And if we can design, or if we have put some thought into making those things, taking those things into consideration while we had done the initial design, then what would have happened is that those costs, those maintenance costs and those service costs, they would have been less. And overall, maybe that total our expense or whatever you call it efforts would have been less. And then of course there are these tax, insurance, etc. They are also part of the cost. So how do we do that? Because in the life cycle cost, the construction takes maybe 2 years, 3 years. Then you have an operation and maintenance for between 50 to maybe 100 years, where you do maintenance and maybe some repair, refurbishing, and then you demolish it. So how do we combine the expenses over say 50 years to arrive at a single number? So that is where we apply the concept of time value of money. I mean, for those who are uninitiated, people otherwise most of you know that I'll just go at, I mean, I'll just explain it a little bit in detail, that what we do is we put all the expenditures over the various years and bring them to the start of the project value by applying the concept of net present value. Now, what is net present value? Suppose I have 100 rupees and I invest it at 5% per rate per annum interest. Then it would become 105 rupees at the end of one first year. The same one, after the second year, it would become another year. Again, I multiply it by 1.05, so it becomes 110.25 rupees at the end of the second year. And that way, at the end of the nth year, it would become that 1 plus 0.05 or whatever to the power n, where n is the number of years. Conversely, if I want 100 rupees at the end of first year, then what I am supposed to do now? I have to have 100 by 1.05. That is 95 rupees I need to spend or save today. Similarly, what I have to spend after 2 years, if I have to spend 100 rupees, so now I need 90 rupees. And then I invest it at that 5%, and at the end of that second year, it will become 100 rupees. So that is called the formula of net present value, NPV. The formula is the standard P by 1 plus R raised to the power n. So this is where this rate of interest is generally referred to as the discount rate, and this whole computation procedure is sometimes referred to as the discounted cash flow. So that way, the construction cost, the operation and maintenance cost, and then the demolition cost at the end of the life of that building or structure, we can come up to a single number. Now, there are catches. So this is an example. I mean, just like that, it's a single one span of a composite bridge. And I have made some assumptions, like say yearly, it's about 70 ton of steel. So I have made an assumption that yearly the operation and maintenance cost would be 1% of the construction cost, and per annum they would increase by 3%. And a thorough maintenance and repair every 5 years at 5% of the construction cost. Again, 3% annual increase. And painting, so it's a steel structure, so I will paint it every 5 years after the first 15 years. Because first 15 years, you get it, you paint it in the shop, and it's a good painting. But once you come to the site, then you can only thing you can do is that just scrap it and then do some aluminum painting. So you have to do it every 5 years. And that I have again more or less a correct cost. That is about 5,500 per ton, escalating at 8% per annum. And I have considered the discount rate as 10%. Okay. Then if you, it's not much legible, but if I just work it out, then every year I have the construction cost in the first year. Every year I have the operation and maintenance cost. They are low for 4 years, and then because of that 5 years, every 5 years I have to do a thorough maintenance, so it's higher. And because of that escalation, yearly escalation, every 5 years it is increasing. That is, first 5 years it was 10, whereas on the 15th year it has become 14, the same amount. Similarly, the painting cost, first we do it in the 15th year, and then we go on doing it every 5 years. And if you look at it, then you will find that even the painting cost becomes 1254 at the end of 75 years, which is more than the initial construction cost. That's what would happen because of inflation and those things. But then if we calculate the net present value of all those things in that manner, then we would add up to that numbers that we have at the last column. So with the initial construction cost of 180 lakhs, after 75 years, it becomes 248 lakhs. So if I have, say, 2 or 3 alternate designs, then instead of comparing the construction cost, I would consider the that discounted cost of the life cycle, which is 248. The whole problem is that how do you know, decide on the discount rate? Like if you look at that table at the right, if you had considered the discount rate as 6%, then this NPV would have become 400. At 10%, this is 248. If you had considered it 12%, it would have become 226, which means that is very much dependent on that discount rate that you consider, and that's how gives you some, whatever you call it, opportunity or whatever to fudge the design and then show whichever is good or bad. I mean, so that risk is still there, but still it's a method which gives you a much better appreciation for the total money that you would be spending. So that's why we call it that the life cycle costing is a process for evaluating the total economic worth of a usable project segment by analyzing initial cost and the discounted future cost, such as maintenance, reconstruction, rehabilitation, restoration, etc., etc. There are good documents, like one that I have stated here, that US NCHRP report 483. It gives a good, step-by-step method how to work out the LCC of a project. Now, one of the reasons why we do LCC is that to understand the trade-offs. For example, acceptance of a more costly design detail to make the maintenance easier, or spend some more money in a more durable coating, say in a steel structure, in order to reduce the more frequent repainting in the future. And that way we can have a an estimate of these options, not just of the initial cost of the structure, but what we are going to do throughout the life of the structure, and then come up with a design which is acceptable to us. So what we have been trying to do, or we try to do, is to very properly use our limited resource, that is money, in order to get the best out of it. But then this is where we come to the next one, that we have another very highly limited resource, that is our earth, where we are not trying to, even in this design, we are not trying to utilize it to the maximum extent, or we are not showing that much interest or anything on conserving it. So that's where we come to the life cycle analysis. I mean, it's a fact that there has been an over exploitation of earth resources in the last, particularly in the last 100 years, in the last century. And associated with that is that, carbon dioxide content in the air. It's now about 400 ppm, which is just double of what was there in the pre-industrial time. And that is the one that is doing the global warming and all the things. And right now, that is, earlier it used to increase at the rate of maybe 1 ppm per year, but since maybe 1970s, now it's increasing at the rate of almost 2 to 2.5 ppm per year. This carbon dioxide, average carbon dioxide content in the air. How it's happening? Mainly the resource extraction has exceeded the rate of population growth. And during the last 100 years, the human activity has escalated the impact on the biodiversity of the world ecosystem. As a result, the global warming is caused by increasing concentration of greenhouse gases produced largely by forest clearing and burning of fossil fuels. And the consequences is rise in sea level, change in precipitation pattern, expansion of subtropical deserts, retreat of glaciers, and the change in agricultural yield. So here, actually, the environment is an issue, the resource depletion is an issue, and the climate change is an issue. And the changes are escalating, accelerating, and the drivers are global. It's happening everywhere, and whether you do it here, it may affect in another country or some other one country. It does this, produces a lot of greenhouse gases. The other countries are going to be affected. So it's a global phenomenon. Now, let's stay on this for a while before we talk about how it affects our design activity. So the term, from that time onwards, this term of the sustainable development came in. And the sustainable development is an approach to growth and human development that aims to meet the needs of the present without compromising the ability of the future generation to meet their own needs. That means that we still leave something for our future generation. I mean, we don't use up everything. And then, uh, otherwise, like this temperature rising is now, I think it's about 1 degree temperature, that is average temperature rise that has happened from the pre-industrial time. And if it goes like this, then it would be about 1.5 degree by 2050 and almost 2 degrees by year 2100. And that effect of that would be just, this glacial retreat and the corresponding increase in the sea level would be catastrophic.
ক্লাসে বললে তো যাচ্ছি দেখছি দেখছো তো আসছো তো যাচ্ছি
Okay. Like say, the sea level rise, I mean, there are a lot of these IPCC models and those things, but roughly it's been, I mean, people agree that if it goes like this, then the sea level will rise by at least somewhere between 30 to 50 centimeter by year 2100. And, like where we live, I mean, it means it's going to almost, inundate whole of that Sundarban areas. Might even come, because ours are something like, we live at around 4 meter is the level, 3 to 4 meter is what is the elevation of this area. And now, and these coastal areas, often many of them are below the sea level. We have these dikes and those things. So with that increase in this, just the sea level increase because of the global warming, I mean, that would be catastrophic. Leave aside, we are already facing the climate change is right here. I mean, like, this high intensity of rains or floods, not only in our country, but almost even in the uh, developed countries. I mean, that is a sign that it's happening. So, there has been some international efforts on understanding and reversing this climate change over the last 5 decades. It's not that the people are not doing anything, so they are doing. The first one was this Brundtland Commission in 1987 that even commissioned a project, and that document is Our Common Future. So that's the document that defined sustainable development as a development that meets the present needs without compromising the ability of the future generations to meet their needs. I mean, that is a very good thing. I mean, like, making that statement, but to, you know, achieve that, it's a tough job. Then there has been a number of now every year we have these. You find this COP21, COP22, and all those things. One major one was the Rio Art Summit, where all the countries they at least agreed that yes, there is a problem, and we need international policies. The idea was that everyone will, all the countries will voluntarily, reduce uh, their effort of this over exploitation and generation of these greenhouse gases. In Paris conference, that was agreed, and it has become now accepted. There's these three interdependent and mutually reinforcing pillars of sustainability: economic development, social development, and environmental protection. They are connected. You can't have one without the other. And unless you do that, then your future generation is going not, get into serious problem. We'll just talk about one thing. The last item in that sustainability is the ultimately in 2015 that summit in New York, UN summit, they came out with that idea of a 2030 agenda for sustainable development, and then they broke it down into 17 items, what they call the sustainability development goals. Like the first thing is that no poverty. You have poverty, then enough food, and these are the requirements. If you have to have a sustainable world, then the equality. Unless these are achieved, how much we are achieving it is a different thing. But these are the 17 goals that were set up, and for each of them, they have a kind of metric for measuring how much we have progressed, and like that. We are supposed to, we claim that India, we are more or less in um, line with whatever goals that we have set up for 2030. Out of those 17, a few of them we have achieved. We are not achieved, but we are in the process of achieving those things by 2030. Some of them we have not been very, you know, proper. And out of these, this is where we finally come down to design this SDG 9. SDG 9 is innovation, industry, and infrastructure. So this is where we can contribute, or we have to uh, put our efforts in. So that's what, now we again come down to our engineering. So life cycle analysis. Just for our general information, that basically, although greenhouse gas is considered to be the major effect in the rapid infrastructure development, there are other effects of environment that also are there. Just for our information, climate change, which is a contribution to global warming, acidification, the occurrence of acid rain, energy loss through life cycle, eutrophication, that is the release of nitrogen and phosphorus, which leads to algal blooms, radiation, land use, air pollution, resource depletion, water use, and ecotoxicity, the release of toxins that are harmful to life. Out of these, the effect of so-called built environment is most significant on global warming is by generation of greenhouse gases. Now, there are two definitions. One is the embodied carbon, and other is the carbon dioxide equivalent. Now, what is the definition of embodied carbon is that it comes from the direct emission due to chemical reactions as well as consumption of embodied energy consumed to extract, refine, process, transport, and fabricate a material or a product. Like say I want to cast a slab. So I buy a ton of 20 bags of cement, and then I mix it, and maybe I operate a mixer and then cast the slab. I put some reinforcement. So I am not producing any uh, carbon dioxide as such. But then why I'm being blamed, or why this infrastructure development? I mean, it's just a small example. That is the idea of embodied carbon. Actually, carbon means, is the term they use. Actually, carbon means carbon dioxide. Say in case of cement manufacturing, 40% of the carbon emission comes from burning fossil fuel to heat kilns, and 60% comes from the thermal decomposition of limestone into carbon dioxide and lime. So together it adds up to 1.2 ton of carbon dioxide per ton of cement. So that much of carbon you have already consumed, or you have already not consumed, but you have emitted when you are opening a ton of cement. For structural steel, which is another, like what I would say, the material that we use, it is approximately 2.8 ton of CO2 per ton of steel when you manufacture. So when I use a ton of reinforcement steel, I have already emitted 2.8 ton of carbon dioxide. And there is another term that they use, is that other than carbon dioxide, there are other greenhouse gases. So that is just a metric used to compare global warming potential of different greenhouse gases. For example, 1 ton of methane is equivalent to 25 ton of carbon dioxide. And methane is generally produced in agricultural products, in the swamps, and like that. And this nitrous oxide, I mean, 1 ton of nitrous oxide is equivalent to 298 tons of carbon dioxide equivalent. Luckily, we don't produce that much. So what we do now, we have national and international codes, guidelines, and research papers. They are available for carrying out life cycle analysis. The environmental effect analysis is generally done as per the provisions of ISO 14000 series, primarily ISO 14040, the environmental management life cycle assessment principles and framework. And there are two other British codes. One is that BS 15978, and other is that PAS 2080. Because as engineers, we need codes and guidelines to carry out an analysis to finally arrive at a number. So this is a typical life cycle. In terms of where here we are only looking at the carbon embedment or whatever environmental damage that we are doing at what stages. At the material production, you have the raw material acquisition. Then you have this transportation to the production site, then the production of the construction material, and then finally transportation to the construction site. Each of these activities, I mean, you either directly produce carbon dioxide, or you use energy, which, as I have said, that one gigajoule of energy, when we use in our countries, like when we burn coal and produce it, it's equivalent to almost 0.2 ton of carbon dioxide. Then comes the construction. where the transportation of the construction equipments, that's one part. Then use of construction equipments, you burn, um, you use energy, whether directly you burn diesel or you take electricity, and then the construction process. All of them, you consume some energy and therefore you generate some greenhouse gas. Then comes the operation part of it. The operation, the maintenance, and the rehabilitation operation. In a bridge-like structures, there isn't much. I mean, basically, every 5 or 6 years you do a repair, painting, and like that. Whereas in a building, that constitutes something like maybe 70% of the um, 70% of the your final the carbon content is during usage. Like this building, we're using it for 60 years and maybe another 40 years we'll be using it, and the amount of electricity and the AC ventilation, water supply, all these are energy. We are using energy in some way or other, and then again at the end of life, then again the transportation of the equipment and the demolition and transportation of those materials to the demolition site. So all these are the typical parts. For each of them, we have to compute or estimate our carbon usage. Or this is a much, I mean, this is that as per that British code PAS 2080, and this is normally, this nomenclature is nowadays used, where it has like this, now people talk in terms of A1, A2, A3, A4, the same thing, but nicely divided. First part is that what they call the upfront carbon, or sometimes they call it the capital carbon. Then the in use, and last is the end of life. And at the end, that is A, B, C, and then what is there in D is that if you can recycle, if you can get something out of the structure when you demolish it, then that is a negative. You get a credit for that. So that's the that basic chart of process of, this is what is given in that ISO 14000 series. The basic general guideline for such study. You do the environmental inputs, and you do an environmental performance score, maybe so many metric ton of CO2, the CO2 equivalent. Then you do the economic performance and effort score, the first cost and the future costs. Social impact is kind of is subjective, but then some people put some metric into it, and then you combine it. And once you combine it, then you get a score based on which you can like compare your one design with another design. And most important is that you try to reduce the CO2 generation to the extent possible, because it's alarming. So the LCA study involves a thorough inventory of the energy and materials that are required across the supply chain and the value chain of the product, and calculates the corresponding emissions to the environment. LCA thus assesses the cumulative potential of the environmental impacts. The aim is to document and improve the overall environmental profile of the product by serving as a holistic baseline upon which the carbon footprints can be accurately compared. So what you do is that you define the goal and the scope of your study. The important thing is that what are your boundary lines that you would consider. They use a lot of terms. That the basic thing is like, say, from cradle to grave. Then they say cradle to gate, and like that. There are a lot of those sort of terms are used, fancy terms. But basically, you define the goal and the scope. You do the inventory analysis. I mean, like it's called inventory. Basically, the carbon emission analysis and its impact. You try to interpret it to arrive at a solution. Or solution means that arrive at a number or whatever to compare one with your other designs, and other is that whatever are the goals. Like in the buildings, you have these LEED and other of the, they talk in terms of these green buildings and like that. Basically, that is also a kind of an LCA that you are supposed to do within a perfect, within a proper format, and then arrive at a number, and then if that number is within that permissible value, then your building becomes a green building. It's a iterative process, they say, that you do once, and then you look at it, and then you might try to change it, or you can kind of change the scope or a change in goal or scope during the course of the study, and you do some additional collection of data, removal, etc., to arrive at a proper number. This is an important, interesting, chart where the final our idea is to use less carbon, or generate less greenhouse gases. I mean, carbon dioxide is people use carbon and carbonation. So if you look at it, then you find that who can influence is most: the society and the users and the occupiers, because their behavior is the most important thing. Next is the government regulators. In some countries, already these LCAs is a requirement. In our country, I think only there is now a circular from Ministry of Finance, I believe, which says that we should carry out life cycle analysis uh, for big projects. But there is still no requirement or anything like that that you shall carry out. Now, if that happens, then possibly some improvement would be there. Then the financer and the asset owner and manager. So basically, once those things are fixed, then the designer has certain scope, the contractor has even less scope, and the product and the material suppliers have even less scopes. So this is an important thing, that at what level you have to take a decision in order to really reduce the carbon content of a product, I mean, of a structure or a infrastructure or whatever you call it. This is the actual, the design principle for, it's a different subject, but basically they use the terms reduce, repair, reuse, and I think recycle will be the last term I again used type. Basically recycle. That means you come out with a lean but robust design. Don't over design, or more important to that is that don't over specify certain requirements, because if that is specified, then naturally the design would be like that. So the whole idea is that it should be lean but robust in terms of effectiveness, the use of OPC cement. Like even if you use 15% fly ash, your carbon emission gets reduced by about 10%. And consider that we always talk in speak in terms of million ton production and like that. Then of course the less and less use of cement where it's not required. I mean that OPC cement. Similarly, the reduction in the usage of reinforcement steel. In quite some places, your um, other material can be used as reinforcement. And the other important thing is attention to construction process and maintenance needs, so that your downtime, your repair, those things are down. And there are many such things, like say steel. About every year, something like 4 or 5% of the steel that is being totally used is lost in corrosion, and about 10 to 12% of the steel production that happens all over the world, they are not for the new construction, but for the replacement of those corroded steel. So if we can do our detailing and the maintenance in such a way that the out of those, the important thing is detailing. I mean, you have these corners and crevices and those inaccessible areas where you have these corrosions. Once you, if you can to the extent improve that, then what happens is that you can get more number of years out of that steel, and you basically achieve better results. So I would summarize that one is that for carrying out the life cycle analysis, a number of codes and standards are available nationally as well as internationally on these subjects. Besides that, ISO 14000 series, LC has been made mandatory in a number of countries, and as a result, the database and specific software are available for carrying out different aspects of life cycle analysis. A large number of papers and references are available for carrying out these LCAs for bridges and buildings. So one can always refer to that. It's not that something is a new one. And the most important is that for the sake of our future generation, we all have to strive for net zero design and construction. Thank you. Hmm. Yes, yes. Corrosion. Yes. Mm-hmm. Yes, that's Rabindra Setu. And it's in a very good. Now, one of the things about that bridge is that the bridge is above your head. So that's the first thing. I mean, like whatever this traffic, I mean, it's hanging. The carriageway is hanging. So that way, the upper part or the actual structure is in a very good condition. What is the problem is that water ingress through those expansion joints. And yes, expansion joints which have, I think it was done maybe 20 years back or something like that. Last time they changed it. And so that water has ingressed through it, and then it has gone to a, as in, wherever you have the expansion joint on the deck, you have some expansion joint in the surface also, that is on the structure also. And so that has started corroding. We just for your information, we did myself, I think you were also there, myself and Mr. Goshal in 1982 or 83. That was the first time this thing happened. Then they repaired it, again it is started. So they are there. Yes, sir. No, steel structure, maybe I have some general preference for it, but steel structure is more durable, definitely. But one is that it's costlier, and second thing is that if you paint it properly, or if you use these coatings properly, then uh, it stays for many years. I mean, like say, there are steel bridges that are 200 years old and they are still there. Concrete in general, concrete in general is, it's like, because that reinforcement that we put in, that depth of carbonation, it's basically it's called square root of T, where T is that year. That means that in 100 years, the carbonation is going to get in by 10 millimeter if everything is okay. And then earlier we used to put something like half inch, 12 cover. So that way in 70, 80 years, that reinforcement is basically the concrete means basically the reinforcement that gets corroded. And once it corrodes, then the rust is something like, the volume of rust is something like 3 to 4 times the volume of that basic iron. And therefore, it cracks. Once it cracks, then the moisture increases and then that process goes down. That way, concrete structures are, I mean, they are basically made for maybe 100 years. Galvanized reinforcement, or even say in some places they use stainless steel reinforcement. So they are much more durable. I mean, they would give much more durability to the structure. Cost-wise, naturally, concrete structures are, again, initial cost, if you look at it, cheaper. That's why in our country we have so many concrete structures. Net zero, yes, actually people are telling that there are some techniques like they will take the carbon and then put it under the earth someplace and like that. I don't know, but actually that is a technological achievement. But what could happen is that like say this green steel, they are talking that instead of 2 ton per ton, 2 ton of carbon per ton, they would be using something like 600 kg carbon per ton to produce that steel. Even say if we recycle steel, so if we, when we generate, develop steel from recycling, it comes less than 1 ton, the carbon emission, compared to say almost 3 ton for a, when you produce it from the um, raw steel, I mean from, so that way you can reduce, and the whole idea is that maybe that global warming of that, even if we at this present moment, I mean there might be some technological development, but even at this moment, if we can maintain that whatever that global warming speed that is there, or if you can reduce it, that would be a great achievement. Because otherwise, we already, the climate change is here. We can feel it. So, to the extent we might at least, reduce that effect or halt its progress that fast, and thereafter some technologies will be developed. One is that people say that you don't use cement, you use, I mean, not cement, but that OPC. You use more amount of this fly ash and other that that blast furnace slag, those things, and thereby you achieve it. Mm. Mm. Right. No, actually, firstly is that in how many structures do you need that much amount of that high strength concrete? No, no, but then what is the say if you consider how many chimneys you are building compared to say the normal buildings and standard things. For there you would require, but anyway, I mean, like say if you want to maybe 500 kg cement is too much. I mean, like in terms of the heat generation and all those things. So you have to add those other ingredients to achieve that strength. Yes, definitely more research is required, and that attention of these researchers should be also on this environmental. I mean, like uh, I am developing something. Now, what would be the carbon content of that one? That is the whole idea of doing these things. Yes, over design is definitely an issue, sir. And over design and the over design, part of it comes from the specifications itself. And there the designer doesn't have much play. I mean, he or she has to follow that requirement. Mhm. Yeah, that is a no, that way there are sometimes you find that it's more of a design these things that you have two cable trays, one is overflowing with cable and other one has a few cables. So that is your, I mean, that, I mean, you have to do your design properly so that all the items are properly utilized. Mhm. Right. Yeah, they are even standing today. No, there are, even with those earlier codes, I mean, people have built, one example that they give is the Coronation Bridge. It's standing beautifully, and there, I think that definitely the designs, the designers, they took a lot of care in, detailing and going a few above the codes. Okay, thank you.
The audiences who have joined us online can, if you have any queries regarding the lecture, you can place into uh, Dr. Nirmalu Bhattacharya, Nirmalu Bandhopadhyay, sorry. You can either write it in the chat box or you can unmute yourself to place your queries. স্যার এখানে তো দেখা যাচ্ছে না
এই প্যানেলটাকে আনতে হবে আর কি।
We have got one query from Shima Sutrodhar. Sustainable infrastructure that is in line with 2030 targets for climate and SDGs. In your view, how possible are they achieved?
To achieve.
Do you see a concerted and collaborative approach across financiers, material developers, construction parties, and others can make this happen?
Well, it's a difficult task to achieve those SDGs. But then, considering our future generations, we have to do that. I mean, it's a part of, basically, it has to be driven in, particularly in our country, it has to be driven by the government agencies because they play the most important part in our infrastructure projects. Yes, no, Gaudik, there are no, uh, any certain values of baseline carbon. It's the lowest that one has to achieve or one who should try to achieve. Yeah.
Yeah, thanks, Nirmala. It was a great presentation and great to hear from you. Uh, yeah, just wondering, of course, that you mentioned about the finance department apparently introducing a kind of legislation for any major projects to introduce kind of decarbonization or embodied carbon calculation mandatory for major projects. So my question was that is there for any large project? I mean, is it not necessary? Is it not part of the overall LCA and to come up with the final footprint what we are going to achieve for a particular major infrastructure?
There are these guidelines and these codes are there in place, but then how far they are being actually worked on, I am not aware.
That's fine. Thanks.
Particularly for highway projects, they have a very detailed code which talks about this how to work out the carbon footprint for the whole of the highway project. But then how far they are being actually implemented, I am not aware. Sorry.
No, sure, that's fine. One more question, if I am allowed to ask. You also mentioned, of course, the greenhouse effect and the major construction industry is coming from the OPC, and the reduction in the percentage of cement or OPC percentage by supplementing fly ash, GGBS, or silica fume, whatever you call it. So you mentioned about 15%. So is there any optimized study for such large major infrastructure projects where a country like India, actually what we are producing and that major infrastructure we are developing, that what is a minimum mandatory requirement for a particular age of life or the serviceable life planned, like if major bridges must be 100 years. So what is the minimum percentage of cementitious, supplementary cementitious constituents? Is there any guideline that can directly influence the sustainability aspect as well?
No, only thing is only a couple of years back that, particularly in bridge projects, these supplements were permitted. And that too, you cannot use, let's say, this PPC cement. You have to buy OPC and then mix it yourself. That was the kind of requirements only a couple of years back. So that way, it's not there. But then, particularly for developing high strength concrete, people are using silica fume, etc. But no, there are. And other thing is that our country is such a big, widespread that whatever, I mean, the applicable or usage is varies from region to region. So you cannot have a single kind of benchmark or criteria for the whole of the country.
Yeah, sure. Appreciate it. Thanks, Nimrata.
Um, Nirmalada, I want to ask you a follow-up question. As you say that it is possible to achieve 2030 goals for climate and SDGs because we definitely have no choice but achieve them. And government regulations are the first thing that comes to our mind, but often it is very, very difficult to get things done by regulation always. But if you see, there are two sides of it, which makes it a different way of looking at it. One is finance can be the enabler or the driver, which can ask for such achievements and reward them for achieving those targets, which is in a way sustainable finance. And the other is that people are today interested to make such impacts and they really don't know exactly how to contribute. If we can create a movement like where people have agency and they can take initiatives to bring about small, large changes through design, through material use, through operations, or whatever it is, I'm sure we can make difference. I would like to hear your comments, sir.
No, these educational institutions and these sort of, I mean, their main duty or the achievements or whatever you call it is basically the dissemination of knowledge and then making people, aware of these things. So, that way, that how far the educational institutions can do, and I think this has to be in large numbers. Then only, the first is that, that realization or acceptance that this is necessary,
Yes.
the climate change or achieving this sustainable development. Once that is there, or that has got into the head of inside, then you can have the rest of the things, that is the actual working out or the effort in achieving it. But first thing is that one has to accept that. So that
Yes.
acceptance, even I find that, even in the very developed countries, they say that it's hoax. Like in the United States, the president of the United States once said that it is an hoax, this climate change. So that those things are there, and he walked out of that Paris Agreement. So, but in terms of our country, one has to develop that awareness. Once that awareness comes, then gradually rest of the things will happen.
Thank you. Thank you. Thank you.
ল্যাপটপটা পরে দিয়ে দেবো যে আপনি স্যার একটু বসুন। Thank you so much, sir, for your insightful lecture. We sincerely hope that the ideas and views shared during the lecture is going to enrich the young minds. The insightful discussion, the thought-provoking presentation, and engaging interactions with the audience truly enriched the seminar experience for everyone involved. Now I request Professor Shoptoshi Kundu, faculty member of the Department of Civil Engineering, to deliver vote of thanks.
A very good afternoon to all the dignitaries present, the esteemed faculty members, the members from GAABESU, and all the attendees who have assembled in the seminar hall of Department of Civil Engineering for this fifth Professor P.K. Roy Memorial Lecture. At the onset, I express my reverence to our honorable director, Professor V.M.S.R. Murthy, to all the respected deans and the institute functionaries who have actively encouraged this endeavor. Our heartfelt regards to our eminent guest speaker and renowned engineer, Dr. Nirmalo Mukhopadhyay, alumnus, Department of Civil Engineering 1973 batch, for taking out time from his busy schedule and delivering a captivating lecture, which is befitting to this occasion. I also take the opportunity to convey my gratitude to our beloved head of the department, Professor Chaitali Ray, who have meticulously ensured the success of this program. Last but not the least, a huge round of appreciation and humble regards to the Global Alumni Association of the Institute, that is GAABESU, for jointly organizing this lecture series. That was adding a new dimension to it. And every person involved with organizing this event, especially Professor Ashok Adok sir, Professor Sneha Murmu, who have been directly and indirectly involved with this function, and their um, efforts. I acknowledge all of them. Thank you and Jai Hind.
With this, the event comes to the end. Thank you for joining us. Uh, there is just as a token of appreciation, we have a memento, and this memento will be delivered to today's speaker, Dr. Nirmalo Bandhopadhyay, and the memento will be delivered by the head of the department, Professor Chaitali Ray, ma'am. With this event comes to the end. Thank you for joining us.